All right. Index juggling is a very, very simple idea. It's so simple that it can actually be confusing. But the idea is this. If you have, let's call it a tensor. Really, it works for variants that are not necessarily tensors. Actually, call it a variant, because we're going to apply this to things that aren't tensors. Ti. And then think about what happens when you multiply it by Zij, the covariant basis. You get a totally new set of three numbers that are obviously related to the three numbers in Ti, but not the same three numbers, different three numbers. But so closely related that it actually makes sense to denote it by the same letter I. So instead of calling it Sj, to call it Tj, because it's so closely related to this original variant. So that's a good way of denoting contractions with the covariant, with a covariant metric tensor. And of course it works the other way. If you have something with a lower index and you contract it with a contravariant metric tensor, you might as well name the result by the same letter and just place the index at the top instead of the bottom. And once you've done this, and now you have this new object, even though it's denoted by the same letter, with sets, three different consisting of three different numbers. If I were to contract this with a contravariant metric tensor, I'll bet you I'll recover these three values, because I'm basically multiplying by the inverse. Well, let's just see that. If I do Tj, take Tj, and dot it with Zij, not dotted, excuse me, multiply by Zij. And when I say multiply by Zij and there's a repeating letter, it's the same as saying multiply and contract. It's like saying multiply and contract. So when I say multiply by Zij, I mean multiply by Zik and then contract on j and k. Well, now let's remember the definition of Tj. Tj was really, I have to use a new letter, Tk, Tk, Zkj, Zij, and this, of course, is delta ij. Even though the indices are switched from this being a clean matrix product, but because these guys are symmetric, I can think of it as Zji. So it's delta ik, so of course it's Ti. So you can, if you start with an object like this and you contract it with the covariant basis element, if you start with an object like this and you contract it with a covariant metric tensor and you end up with an object like this, three different numbers but related, you can recover the original three numbers by contracting with the contravariant metric tensor. So these operations are inverses of each other. So contracting with a metric tensor is called juggling indices. So in this case it's called the lowering of the index. And this is called the raising of the index. And the two operations are opposites of each other. So here's another example in abstraction. If you have Tij, something doubly contravariant, or hoping and failing to be doubly contravariant, if it's a variant and not a tensor. But an object like this, and you dot it with, not dotted again, contract it with Zik, what you get is a new variant. What you get is 9 numbers that are not at all equal to these 9 numbers. But it's 9 numbers from which the original 9 numbers can easily be recovered. So it's very much related. So it would be denoted by T, K, J. And here the order is super important. K is the first index, right? This is lowering the first index. It's the first index that goes down, so you have to keep track. So sometimes you just put a dot here as a space keeper. I can lower both indices at the same time. T, I, J, Z, I, K, Z, J, M. And the result is a totally new object, but it can be written as TKM. So it's really not a new operation, it's just new notation. Makes everything much more compact, even more compact than it was before. Allows us to save introducing new letters. Previously we would have called this S or some other letter. And then this would have been T, and this is U, and then this is V. But this just allows you to save letters and really remind yourself of how related the objects are. And it just works across the board. So let me give you, I'm sorry if you're running out of your half page. You're not? Good. Okay, so here's a few examples. If you have a vector V, you can decompose it with respect to the covariant basis, and you would end up with contravariant coordinates. I don't know why I chose K, but obviously it doesn't matter. Or you could decompose it with respect to the contravariant metric tensor, ZK. And then you would end up with components that you can easily prove form a covariant vector. Excuse me, tensor. So are these two related, in fact related by index juggling? And the answer is of course, because this is VK, ZKI, ZI, am I right? I just wrote down the definition of the contravariant basis. It's the covariant basis contracted with the contravariant metric tensor. So this right here must be VI, because that's the component of the same vector V with respect to the covariant basis. So of course VI, the contravariant component and the covariant component, are related by index juggling. That's really good news, because otherwise maybe you would have to use two different letters. So that's another example of index juggling. And the very first example, you've already seen it, it's right here. Remember when we defined the contravariant basis? It was defined as ZJI, ZI. And do you see right here? So for us it was a definition and a surprising use of the same letter as for the covariant basis. Maybe it was momentarily surprising. But now you can just see it as a special case of index juggling. These three vectors are different from these three vectors, but very much related. You can go from this one to this one by contraction with the metric tensor, and from this one to this one, which you're seeing right here, by contraction with the metric tensor. So this is just a special, this was your first example of index juggling. So I can write things with upper indices or lower indices, and the fact that you use the same letter indicates the relationships between two things. So index juggling makes for a lot of great looking expressions. Let's dot two vectors. Let's dot two vectors. U and V. Extra credit for anyone. Oh, there it is. Oh, there's a second one. Okay. I was lying about that. All right, I'm sure you remember this. U dotted with V is Z, I, J, U, I, V, J. Everybody remembers this? Of course you do. But now invoke the index juggling convention. And you can write this as U, J, V, J. Isn't that right? You can also write it as, it's just lowering the index on this. ui vi. And this is a second instance today of something that looks as simple as if the basis was orthonormal. Remember, with respect to the orthonormal for an orthonormal basis, the dot product has the equation u1 v1 plus u2 v2 plus u3 v3, only if the basis is orthonormal. If the basis is not orthonormal, then the metric tensor figures very prominently, plays the key role actually. But now with the index juggling convention, the appearance is as simple as if the basis was orthonormal. But of course the algorithm for calculation is embedded now in the placement of the index. It's not that the metric tensor disappeared, it's just that it's now denoted by the placement of the index. It's super nice. Super nice. And of course, if you have question, yeah.
Yeah, I'm just confused on the V, why the index is an upper one.
Which here?
No, on the V on the right. Yeah, that one.
It is upper.
But I'm confused why.
So are you okay with this expression?
Yeah.
The data product equals this?
Mm-hmm.
And then just look at this part. Just this part right here.
Oh, you just juggled one.
I lowered the I.
I got it.
And got this. And then I looked at it this way. And I lowered the J.
Alright, got it.
Yeah. So in fact, here is sort of an abstract note. If you have an expression like this, for example, SI TI, this contraction, then you can also write it as S with an upper I, T with a lower I. You can write it as, I'll prove it in a second. It equals this. And if you think about it, so in about one day, your eye will almost look at these two expressions as indistinguishable. But for now, it actually means, well, it will continue to mean something, but you just have to take your time. Because I can write this as S-I Z-I-J T-J. Do you agree with me? This is me expressing Ti as T with a lowered index, index raised. So this is a way to write Ti with an upper index. And now I will mentally group it this way, and this will become Sj. So S upper J, T lower J. So it's SJTJ, and now rename it back to I, SITI. So with the dummy index, you can always do this. Not always. Can I show you one example when you couldn't do it? We're going to discuss it in much greater detail in just a few minutes. But if you had something like this, now we're going back into space and thinking about what happens from one point to another. Si dti as a function of z's. dzj. Could you do this? Raise this I, lower this I? Across the derivative object? Across the derivative? You could not. Because lowering this I is the same as the contravariant tensor making an appearance under the differentiation sign. And because its derivative is not zero, it varies from point to point. It doesn't come out of this unscathed. So you cannot juggle indices across the derivative. I think I'm overloading you a little bit, but you should know this. So just remember that juggling indices is this moving of the contravariant tensor from one object into the other. Kind of a matrixy sort of thing to do. If you have a tensor identity, if you have a tensor identity with a live index, let me write down a crazy one. Si equals Tij K, U, K, J. I might even put the dots. Now we have to start putting these dots so that every index has its own slot, and it can move up and down that slot. But this could be a tensor identity coming from somewhere. I can certainly contract both sides of this identity with ZIM, which means that the index I would come down on both sides as the index M. And then I could once again rename it from M to I. So I can lower a live index on both sides. And on this side it has to look like this. Here when we, I went back to I. So that's lowering the index on both sides. And of course these K's, this one can go up, this one can go down. And these J's can do this. Okay, it's all the tensor from the tensor calculus point of view, the equations are completely equivalent because they evaluate to the same thing. But if you zoom down to the actual numbers that are being used in a multiplication, they're completely different. It's like a matrix being extracted out of this object and stuck into this one. Let's lower the index, one of the indices on the metric tensor. Why not? See what we get. That's maybe deserves to be on its own board because it's supremely confusing. And then you think about it for a long time and you get used to it, and then it becomes simple. Z, I, J. Let's lower the J. You always have to ask which index are you lowering. Let's lower the J index, the second index, which means contraction with Z, J, K. And the answer is Z, I upper, K lower. That's how you lower the index on the metric tensor.
But if that was Zij, if that was Zij times Zji, then it's completely.
Then that would be 3.
Right.
Okay? So here comes the confusing part. How come you never see this sort of thing? So what's this contraction? What's another way to denote this contraction?
Shouldn't that be the Kronecker delta?
Yeah, it's delta. That's why the Kronecker delta is the metric tensor. It's completely equivalent to the metric tensor. So this is also delta IK. So the Kronecker delta is just another form of the metric tensor, even though it consists of only ones and zeros. But it's just another form of the metric tensor. A little confusing, but you just get used to it. So that's why the Kronecker delta and the metric tensor are basically one and the same object with a changed flavor of the index. There's a stunned silence, which it should be. Let me do one other thing. This might confuse you more, or it might make things easier. Let's lower the other index on I. On the delta. Let's do delta IK. Now you don't have to pay attention to the order of these, only because these things are symmetric. So if you should maybe be initially careful and keep the order, but then you quickly learn that it would be much more confusing if I were to show it right now than if I didn't show it, because it's almost trivial. But let's lower the I. Z, I, M. No, whatever. Z, I, M. And the answer will be delta MK. That's what delta with a lowered index means. And again, I'm going to go back and say, well, what's another way to denote this? Oh, this is delta, right? We know what delta does. It just renames an index. So another thing you can call it is Z, Km or Mk, doesn't matter. I'm just really taking advantage of the symmetry of this object. ZMK. Once again, you see the equivalence between the delta and the metric tensor. And you can even use this notation. as long as this does not mean zeros and ones to you. So it's actually quite common, although, do I disagree with it? I'm not sure if I disagree with it. Maybe it's not a bad way of denoting it. Delta and k sometimes means the metric tensor. So actually in a lot of your engineering books that just all live in Cartesian coordinates and the placement of the index doesn't matter, but the Kronecker delta appears, very frequently if you just look at this object and interpret it as the covariant metric tensor, which is what it is, and not 1 if m equals k and 0 otherwise. If you just interpret it as the metric tensor, a lot of those equations will all of a sudden become valid in all coordinate systems, as long as this has the proper interpretation. Is this a little hard to take? It is. I remember myself learning this. It just takes a moment.
Does it work for the contravariant?
Of course. Yeah. Just raise the index on this. On the one hand, you get z with one index raised, this sort of thing. But on the other hand, because it's the inverse, it's delta, and then raise one more index. You know, and well, you can just even think of it this way: just take the k and raise it. Here you get the z with two upper indices, and here you get the delta with two upper indices.
How is that true though? In polar coordinates, cylindrical coordinates,
Yes.
the metric tensor, covariant metric tensor, has an r squared in it.
Yes.
How is it equal to? The Kronecker delta does not have r's in it.
Which Kronecker delta? With two
Covariant,
lower indices? Yes, but this no longer means 1 if m equals k. It no longer means that.
What is it? How do you compute that?
Well, it's the metric tensor.
So there's no way to separately compute that and make sure it's equal to the metric tensor.
Yeah, there isn't. It's just the metric tensor. Or you could compute this, which is this,
And lower the index.
and then lower the index, which means this. And now this is 1, right? So how do you want to think about it? Right? So you can think of it as z lower ij, or you can think of it as delta lower ij. So in fact, delta and z basically are the same object. So you thought they were different, but they're actually the same if you use the index juggling convention. Beautiful equivalence. So basic and works so well that you will actually just start moving indices without giving it much thought, and sometimes even make a mistake, because it becomes such a second nature thing to do, to just say, let's lower the indices of both sides. You will forget that it actually involves multiplying by the metric, which cares very much about whether it's inside or outside of differentiation. All right? That's index juggling. Let's talk about, yes?
So I think I asked you this before, but what's the point of having these two different kinds of bases? Like, is it just for the math to work out? Like covariant and contravariant?
It's for two reasons. Number one, it's nice to be able to write things like this, right, without the metric tensor appearing. That's number one. Number two, in continuum mechanics and probably in other examples, you can write the equations in covariant coordinates, and then you can try and raise indices on both sides, and because there's differentiation involved, it won't be just as simple as raising the index, because there will be additional terms, because the metric tensor will have to come out of the differentiation sign, and it will actually cancel a lot of terms, and will be either much simpler or much more complicated. So for Eulerian fluids, there is this theorem that's called conservation of vorticity. Yes, conservation of vorticity. In contravariant coordinates, so vorticity I think is denoted by the letter omega. In contravariant coordinates, conservation of vorticity will look like this. In covariant coordinates, there will be two additional terms. So depending on the situation, one basis is more convenient than the other. But they're, in a sense, equivalent, because you can get from one to the other by index juggling, which is just an index in a matrix product, so to speak, and nothing else. But two is better than one. Just like having two hammers in your tool bag, one a little heavier, one a little lighter. Two is better than one. And yes, makes the math work out much more nicely. All right.